see many students are not here, but we will proceed. I'm planning to solve problems from chapter 36 together, and then we will start solving problems from the practice exam that I have posted in Blackboard. So this is a very important practice, I guess, review and practice at the same time. So let me I just wanted to finish the last two slides. Okay, so remember we said if you have a double slit experiment where you have coherent light coming to the two slits and you have a screen at a distance L, you produce a pattern fringes of maximum intensity and minimum intensity, and we said that the fringes that we obtain maxima and the minima are given by this equation. So the maxima are when the difference between the path length R2 minus R1 delta is equal to d sine theta when it's a multiple of lambda, m lambda, where m is the order number and can be 0, plus or minus 1, plus or minus 2, and so on. So these will give you the maximum intensity on the fringe pattern, we have minima when d sine theta is equal m plus 1/2 times lambda, where again m is the order number. It's different from the order number for the constructive interference. The destructive interference m is also 0, plus or minus 1, plus or minus 2, and so on. So these are the two main equations. And then later on, we've seen that in certain situations, if we have a small angle theta, we were able to make an approximation that sine theta is approximately equal to tangent theta, okay? And from that, we were able to obtain the position of the bright spots. So y bright is L m lambda over d. So this is so for a small angle theta. So let's say 15 plus or minus 15 degrees or less. We can use this approximation. For the dark spots, the position of the dark fringes is given by L m plus 1/2 lambda over d. Okay. And last time I stopped at the mathematical equations for these waves. A wave can be represented by a mathematical equation. It can be sine or cosine, doesn't matter. So we can write the wave intensity is equal the amplitude ym cosine kx minus omega t plus a certain phase phi. Okay. So k is what we call the angular wave number, which is 2 pi over lambda, 2 pi divided by the wavelength. Omega, you are familiar, it's the angular frequency, it's in radians per second, and it's equal to 2 pi over t or 2 pi f. So f is the frequency in this case, which is 1 over t, and omega and f are related by omega is equal to 2 pi f. Now, a wave speed is how fast this wave travels in a medium. For light, we know the speed is c, which is approximately 3⁻⁸ meters per second. But for other, for example, sound, it travels about 342 meters per second in air. So the wave speed is given by v is omega over k, or lambda over t, the wavelength divided by the period, or we can just use lambda f. So if you know the speed of a wave, for example, the speed of light is c, okay, and you know the frequency of the light, you can determine the wavelength from this equation. So for light, speed is 3⁻⁸, and for sound in air, approximately 343 meters per second. Okay, so let's if we want to see that, so this is a wave that is traveling in space. Okay, so this is the wave speed, and if we freeze the wave at a certain instant, okay, so we take a snapshot okay, and we plot the amplitude y versus the position, this is what we get. We get what we call a snapshot. So in this case, the x-axis is the x position, and the y-axis is the intensity of the wave. It can be, for example, the electric field or whatever. Okay, so a period along the x-axis is equal to the wavelength lambda. So the periodicity in space is given by lambda of the wavelength. Now the other thing, if we take a single point, for example here, and we follow it as a function of time, and we plot y as a function of time, this is now different. It's not y as a function of position. We are just plotting y at this point here, but as a function of time, to get what we call a graph as a function of time. So this is a graph of the position y of this point here that is going up and down as a function of time, and in this case the period in time is t. So the period in space or in x is lambda, wavelength, that's what we call the wavelength, and the period, the period is how long it takes for the cycle to repeat itself. Okay, so in time it will become the period t. All right, so actually sound waves and light waves can be modulated or can be modeled by this equation. So an amplitude times sine or cosine kx plus or minus omega t plus a certain phase phi. Okay, so if we have two waves coming, like in the case of the slit, we have a wave coming from slit S1 and a wave coming from slit S2. So both of them are waves that we can express mathematically. We can, in that case, write the following equation. Okay, so let's assume that wave S1 is given by S cosine x minus omega t, and the wave S2 is same thing except we have a phase phi, phase difference phi. So here the difference between the two waves is the phase difference phi. Remember, we said in the previous lecture that the phase difference can be obtained by determining the delta divided by lambda, which is the wavelength, times 2 pi. That will give you the phase difference. So let's assume we know the phase difference, okay? And we want to add a cosine plus a cosine. You know from trigonometry that cosine alpha plus cosine beta is given by 2 cosine alpha plus beta over 2 times cosine alpha minus beta over 2. This is a trigonometric equation. I'm sure you have seen it before in math. So if we apply this to these two waves, this is what we obtain. We obtain, so the addition of the two waves, S1 and S2, will give us 2 times Sm, which is the amplitude, times cosine of the phase divided by 2, phase difference divided by 2, okay, times cosine kx minus omega t plus the phase divided by 2. So notice that kx minus omega t, except now the summation of the two will give us the phase phi over 2. But now this is the amplitude. Notice the amplitude is a function of the phase difference. So phase difference. So let's take situations. Let's take the phase difference to be 0. There is no difference between the two waves. The phase difference is 0. Okay. So what is cosine 0? Cosine 0 is 1. So now, if you add wave 1 and 2, the amplitude is twice the amplitude of each of the waves, 2Sm. Alright? Let's take, for example, 2 pi. Phase difference of 2 pi. 2 pi divided by 2 is pi. Okay? Cosine pi. So let's get. So here, 2 pi divided by cosine pi. Cosine pi is what? Minus 1. Okay? So we obtain minus 2Sm times this cosine. Now, let's take pi. Let's take the phase difference of pi. So now we're going to have destructive interference. Remember, we said if the phase difference is 0, 2 pi, 4 pi, 6 pi, we have constructive interference, amplitudes add. But if the phase difference is an odd multiple of pi, like pi, 3 pi, 5 pi, and so on, then we obtain destructive interference. So look at what happens to the amplitude. Pi divided by 2, that's pi over 2. What's cosine pi over 2? 0. So you obtain the amplitude becomes 0. This is where we have destructive interference. Basically, the waves cancel each other. So the waves cancel each other, and we obtain destructive interference. So if the phase difference P is a multiple of 2 pi, we get constructive interference. The amplitude is actually twice the amplitude of each of the waves. But if the phase difference is an odd multiple of pi, pi, 3 pi, 5 pi, can be also minus 3 pi, minus 5 pi, and so on, then we obtain destructive interference because this amplitude here goes to 0. So this is the math behind constructive and destructive interference. Even though this is optional, I wanted to explain it because it gives you a good mathematical idea of what's going on. So you're adding two cosine or sine waves. There is a phase difference between them. According to this phase difference, you will have this amplitude. So, okay. Any question about this chapter? Because that's all what we need to cover from this chapter. We want to solve problems from this chapter. Ready? Anybody has a question? Okay. More than half the class are not here, which is very strange because we are planning to review. All right, so let's start the Kahoot. And okay, so this is going to be quick practice because I like to move to the review from other chapters also. So we'll start. Okay. Okay, so please enter the Kahoot. We will do this practice together. Okay, so here we have two slits. They are separated by a distance d of 0.32 millimeter. A beam of wavelength 500 nanometer strikes the slits, producing an interference pattern. Determine the number of maxima observed in an angular range if theta is between minus 30 degrees and plus 30 degrees. So how many maxima in the fringe pattern we will see between minus 30 and plus 30 degrees. So I'll give you 2 minutes to do this, 2 minutes. Okay, so let me increase the magnitude. Go ahead, please practice, and if you like to join your neighbor. You can refer back to the equations from the slides. Want to? Join, please. Discuss, if you want to discuss with your classmate. Okay. Ready? Okay, the code is, come on. The code is 4489380. Anybody finish? Anybody? يلا جماعة يلا. This is easy question, In this chapter we have only 4 equations, Lambda is d sine theta is equal to m lambda, or d sine theta is equal to m plus 1/2 times lambda over 2. And we have the equation for y. Anybody? Anybody finished? All right. Okay, Jama. I want to move through this. Anybody finished? Okay. Well, we have some who finished. Okay. So let's go and enter. Choose between A, B, C, or D. Good. 6 out of 12. It's not bad. All right. So let's look at this problem. Okay. So we want to determine the number of maxima. What is the equation for the maxima? We know. So D. Oops. We know the equation for the maxima is lambda or delta d sine theta is equal to m lambda. All right. So here we are given lambda, we are given the wavelength, okay, and producing the interference pattern, determine the number of maxima. All right. So we are not given d. We are given d. We're given lambda. Okay, we have d. All right. So let's try to determine m. If the angle theta is 30 degrees. All right. So we can write that m is equal d sine 30 divided by lambda. So that is 0.32 10 to the minus 3 times sine 30 divided by lambda, which is 500 10 to the minus 9. Okay. When you do that, you find m is equal to 320. Correct? You find m is equal to 320. Does that mean we have 320 bright fringes? No, because m can be positive or can be negative. So let's write m. M can be 0, plus or minus 1, plus or minus 2, and we can keep doing this until we get plus or minus 320. So how many bright fringes we have? The number of the bright fringes is 320 times 2 plus 1, because there is the 0, 1. When m is equal to 0, which is in between, so this is m0. So if you add all of these, you get 320 times 2, but you have to add the one for m equal to 0. So you get 641. So you get 641. Clear? واضح? Okay, next problem. All right. Next. All right. So 2 minutes for this one also. 2 minutes. So a laser beam incident on two slits with a separation of 0.2 millimeters. A screen is placed 5 meters from the slit. An interference pattern appears on the screen. If the angle from the center fringe to the first bright fringe to the side is 0.181 degrees, what is the wavelength of the laser light? What is the wavelength? This is easy. So let me magnify it. Ibrahim. That's enjoyable, isn't it? نعم. Static. The code. It's 4489380. 4489380. Yalla, quick, so that we can cover as many problems as possible. This is easier than the previous one. Discuss with your neighbor. See if you agree. Okay, ready? Who's ready? Oh, good number are ready. Okay, so we'll move. Okay, choose between A, B, C, or D. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, what's going on here? That means there is something wrong. That means there is something wrong. Okay, so here we have a distance D between the two slits, a beam of wavelength lambda. Naam? Is that another question? Oh, sorry, that's okay. Is this question? All right, okay. So a laser beam is incident on two slits with a separation of D, 0.2 millimeters. The screen is 5 meters away from the slits. This is L. And the interference pattern appears on the screen. If the angle from the central fringe to the first bright fringe to the side is 0.181 degrees, what is the wavelength? Okay, so we know for the bright fringes we have delta is D sine theta is equal M lambda. So the central fringe is M is equal to 0. Okay, oops. So, and the first bright fringe is M is equal to 1. So, all right. So M is equal to 1. So the angle here, theta, this is the angle theta. So for M is equal to 1, we get D sine theta is equal to lambda, and they want to determine the wavelength. So lambda, which is equal So lambda is equal to d sine theta. Okay, when you do that, you find that in this case, d sine theta, you get 632 nanometers. So let's see why did we have many wrong answers here. Oh yeah, so sorry, so the correct answer is D. So 10 are correct. Sorry about that. Sometimes I make mistakes. Okay, good. So I'm happy. All right, so let's go to next question. Next. So sorry for now, the scores are probably wrong. Okay, so here is a little bit longer question, and you are only supposed to answer question A. So I will give you 2.5 minutes for this one. It's not actually difficult. So let me increase the... two double slit experiment, two parallel slits with a slit separation of 0.1 millimeter are illuminated by light of wavelength 589 nanometer. The interference pattern is observed on the screen located 4 meters from the slits. What is the difference in path length from each of the slits to the location of the center of the third order bright fringe on the screen? Third order bright fringe on the screen. So, okay, who finished? Who's finished with A? Good number. Good number. Okay, so I'm going to start. Choose between 1, 2, 3, A, B, C, or D, and hopefully this is not there is no mistake now. Correct answers, 3 incorrect answers, and we have 2 did not answer. Okay, so let's do this problem. No. Okay, so here we have 2 parallel slits with a slit separation of d 0.1 millimeter. And the wavelength is 589 nanometers. The interference pattern is at distance L, 4 meters. What is the difference in path length, which is delta, from each of the slits to the location of the center of the third order bright fringe? So let's draw. Okay. So remember, M is equal to 0 at the center. the first order m is equal to 1, okay, m is equal to 2 is the third one, and m is equal to 3. This is the third order. When we say order, we mean m. So this is m is equal to 3, but notice it's the fourth right fringe. 1, 2, 3, 4. So m is equal to 3. Okay, so we write this is equal d sine theta, which is m lambda, but we don't need anything. We need m and lambda only. So delta is equal to 3 times lambda. Okay, so if we do that, we find that 1.77 micrometers. So this is 1.77 micrometer. So the correct answer is A. Okay, question B. What is the difference in path length from the two slits to the location of the center of the third dark fringe? Third. Now they did not say order. They said the third dark fringe. So now let's do the drawing again. Okay, so let's use a different color. Okay, so this is the first dark fringe. This is m equal to 0. Because what do we have? We have lambda is d sine theta is m plus 1/2 lambda. Okay, so for m equal to 0, we get the first dark fringe. For m is equal to 1, we get the second dark fringe. And for m is equal to 2, we get the third dark fringe. And here they said the third dark fringe. So m now is equal to 2. And we can write the path length difference. Delta is equal to 2 plus 1/2 times lambda. And when we do that, you find that in this case, this is equal to 1.47 micrometer. Remember, there is a difference between the order, m order, or the order of the fringe, and the number of the fringe. So here, even though this is the m order of 2 for the third dark fringe, m is equal to 2, and this is the third dark fringe. So do not confuse the two. Always draw to know where you are. Okay. So I think let's do at least one more problem from this chapter. This is easy. Okay, so let me skip this one and go to this last one, I think. Last interesting one. Next. All right, so we'll give you 2 minutes for this one. Okay, 2 minutes. Let me enlarge it so you can read it. And you're only supposed to answer question A. Notice now it's asking for the phase difference. And remember, phase difference is the path difference, delta, divided by lambda times 2 pi. That's how you get the phase difference. So first of all, you need to find the path difference divided by the wavelength lambda and multiply by 2 pi. Just a few minutes, please. You have class now or what? All right. Who finished? Only two, huh? Anybody? Okay. And let's start for the sake of. All right. So so choose between A, B, C, or D, and let me do this next. So enter your answers. We have 11 correct answers and 2 incorrect answers. That's amazing. All right. Okay, so now next problem here. Okay. So we're given L, we're given D, we're given the winner is 59782. Okay. So let's see. Calculate the phase difference between the two wave fronts arriving at P when the angle theta is 0.5 degrees. What do we know about the phase difference? We said the phase difference is given by the path difference divided by lambda times 2 pi. So we need to determine the path difference. The path difference, we said, is approximately equal to d sine theta, because notice L is much larger than the separation d, so we can use this approximation. So we can write that now the phase difference becomes d sine theta, which is given 0.5 divided by lambda times 2 pi. And when you do that, you find that in this case the phase difference is 13.2 radians per second. 13.2 radians per second. Okay, so